Hey everyone, and welcome to today's Explainer. Every single day, millions of medical scans are taken around the world, but interpreting them relies almost entirely on the limits of human endurance. Well, I am absolutely thrilled to guide you through some truly groundbreaking research today. We're going to explore the absolute cutting edge of medical technology, focusing specifically on how we can make artificial intelligence a transparent, deeply trustworthy partner in cancer diagnosis and treatment. For a long time now, the conversation around medical AI has been all about its potential, right? But today, we are looking at the concrete structural innovations that are finally turning that potential into a safe, reliable clinical reality. We're unpacking research that introduces explainable and uncertainty-aware deep learning for incredibly accurate tumor and organ segmentation. So get ready, because the science we're about to cover is literally changing how we approach life-saving medical imagery. Let me ask you something right out of the gate. Would you trust a black box with your cancer diagnosis? It's a critical, almost chilling question, isn't it? I mean, in high-stakes medical decisions, an AI system that just spits out an answer without showing its work, that's simply not good enough. When we're dealing with human lives, doctors absolutely cannot blindly follow an opaque algorithm. We need to know exactly why the AI made the decision it did, and honestly, just as importantly, we need the AI to tell us when it isn't sure. This is the real-world problem that has held clinical AI back for so long. Okay, let's dive into this. Think of standard AI like an overconfident student who guesses on a test rather than just admitting they don't know the answer. It acts as a black box, and critically, it completely lacks uncertainty estimation. It gives you an answer, even if the data is messy or limited, with entirely unwarranted confidence. Trustworthy AI, on the other hand, is the new paradigm we're exploring today. Trustworthy AI is explainable, it's uncertainty-aware, and it is robust. This means it can actually estimate its own prediction uncertainty when it's faced with limited training data. It's basically the difference between a system that guesses in the dark and a system that maps out exactly what it sees while honestly admitting where the shadows are. Section 1. The Medical AI Trust Problem. Section 2. NETRAM, Perfecting Radiotherapy Planning. So, to map out the macro world of CT scans and actually solve this medical trust problem, researchers developed a project called NETRAM, which stands for Neural Architecture for Trustworthy Radiotherapy Assessment and Management. It's essentially our macro map. And its first major hurdle? Protecting OARs, or organs at risk. You see, the head and neck region is packed with vital, healthy organs and tissues right next to potential tumors. When a patient undergoes radiotherapy, the goal is to blast the tumor while perfectly preserving these organs at risk. Precisely mapping these OARs is quite literally a life-or-death necessity. If the AI draws the boundary even slightly off, a patient could suffer irreversible radiation damage to healthy tissue. And that is exactly why NETRAM's focus on robust, trustworthy contours is so absolutely vital. Let's move to NETRAM and see how this builds. NETRAM operates in two distinct stages to ensure maximum explainability. First up, it uses wave mix. Think of it as a highly specialized filter that spots irregular anatomical shapes. This is paired with a patch-based prototype network, forcing the model to be fundamentally explainable in its nature. Then in phase 2, it utilizes a deep learning U-Net architecture for semantic segmentation, armed with an attention loss function. In plain English, this acts like a spotlight. It forces the AI to focus heavily on localized features, using established medical domain knowledge to create incredibly robust boundaries for both the tumors and those critical OARs we just discussed. Now, theory is awesome, but results are what actually matter in medicine, right? When put to the test using standard metrics like IOU and DICE scores, which basically measure how perfectly the AI's drawing matches a human doctor's, the results are just incredible. NETRAM doesn't just match current models, it outperforms the state of the art. And importantly, it did this not just on some freely available head and neck cancer CT dataset, but on messy, real-world clinical CT data from Ames and JNCH Bhopal. This really proves its real-world clinical superiority. Section 3. DRISHTI, Mastering Histopathology Complexities. Okay, now we're going to transition from the macro level of CT scans all the way down into the cellular micro territory with a project called DRISHTI, which stands for Diagnostic Reasoning and Intelligent Segmentation for Histopathology Imaging. To really understand this microworld, we need to quickly define histopathology. This is the manual identification of abnormal tissue structures, specifically malignancies like cancer, by examining microscope slides. Right now, this process is heavily reliant on manual human effort. Pathologists follow strict WHO guidelines, but because it relies on human expertise, there's often variability between different observers. And look, even though digital pathology has improved the workflow, diagnosing complex cases still requires immense, grueling manual labor. Now, what's really interesting about this slide is understanding why this microscopic world is so remarkably hard for standard AI to process. It's because histopathology images are incredibly messy. Imagine trying to read a map that has been folded, stained with coffee, and torn. That is exactly what a computer sees when looking at physical tissue slices. The AI has to deal with massive physical ambiguities, variations in how the tissue was stained, artifacts from preparation like tissue folding, tearing, and compression. Add to that the imaging inconsistencies and the inherent biological variability in the tissue architecture itself. Standard deep learning models might show a lot of promise in a pristine lab setting, but they fail entirely to account for this massive physical ambiguity in the real world. Enter the DRISHTI solution. This is a brilliant indigenous Indian solution that embeds an expert pathologist's domain knowledge directly into the system using vision language models. To handle that messy, coffee-stained map reality we just talked about, it uses something called aleatoric uncertainty modeling, which actually is just a mathematical way for the AI to honestly say, hey, this specific part of the image is just too blurry to call. It safely navigates the inherent randomness of tissue samples. And here is the true game changer. DRISHTI doesn't just confidently find tumors. It takes things a massive step further by automatically generating comprehensive pathology reports, saving doctors countless hours of manual paperwork. And the scale at which they are proving this, it's staggering. 2,000. That is the number of whole slide images being used to validate this approach. This massive dataset comes straight from AIIMS Bhopal and was meticulously scanned at IISER Bhopal. DRISHTI is being specifically validated on head and neck cancer, which, as you might know, is highly prevalent in India. By using an enormous local data set of 2,000 whole slide images, the researchers are ensuring that this indigenous solution isn't just theoretically sound, but practically forged in the realities of the local clinical environment. Section 4. Building trust in clinical AI. So the crucial point is this. By combining macro protections like NETRAM with micro-level cellular analysis like DRISHTI, this research represents a massive leap forward. But the ultimate objective isn't to just leave this sitting in an academic lab somewhere. No way. The goal is to develop robust, commercially viable software. The researchers aim to validate this trustworthy AI framework across 5 different hospitals throughout India, expanding it to handle multiple cancer types. They are building a tool designed to empower doctors across the country with robust, transparent data, which is going to completely transform the standard of care. I want to leave you all with this final thought. If AI can now perfectly explain its reasoning through tools like WaveMix, and if it can mathematically admit its uncertainties when looking at a torn tissue slide using tools like DRISHTI, well, what other impossible medical hurdles can we finally overcome? We are truly entering an era where AI is no longer a black box, but a transparent, reliable medical partner. Thank you so much for joining me for this explainer on NETRAM and DRISHTI. Keep questioning, keep learning, and I'll see you next time.